much
Okay, hold on.
exciting. Still very
Turn the video up.
That's pretty much standard. Okay,
Oops.
let's get rolling. What are we doing tonight? Oh, tonight's Biochem 1? I love Biochem 1. Let's get down and dirty with some Biochem 1.
Let's get down and dirty with Biochem
All
1.
right. Well, enzymes.
Doesn't that sound
Enzymes
fun?
are.
Okay.
Yeah,
Keep on
there was an
doing
enzyme
this.
passage allegedly
Just
too
gotta
on
make
one
sure.
of these
I'm gonna
recent
stand here
tests.
for 1 second.
And what does an enzyme
Okay,
do?
there it is,
Well,
there it
we're
is.
about to
Okay.
get figure
Yep.
that out, I suppose.
Yep,
So an
well,
enzyme grabs two substrates, and then it induces a fit, which means when it binds, it actually changes conformation and squeezes these two bad boys together. Got it? Good. Thanks, Ian. So induced fit means you snap these bad boys together and you make a product. So substrate 1, substrate 2, bam, you make a product C. And that part of the enzyme right there is called the what? You guys need to be more active. Get it? Active site. And we should know the most common amino acids in the active site of an enzyme are what? What? What are the most common amino acids in the active site? Who doesn't love little sty? No, Malec. Malec. Malec are the amino acids in the alpha helix. That's all right. Sty. Serine, threonine, tyrosine, folks. Why, you may ask? Because they have hydroxy groups, I tell you. Hydroxy groups important? Yeah, they're pretty damn important. I love little hydroxy groups now and again. So now we understand where that comes from, don't we? Mm-hmm. Okay. Enzymes, well, what happens? We have competitive inhibitors, and what do? They compete. Hey, I'm competing. I want to get in here. Let me get in here. Okay. But if I add more substrate, I can overcome a competitive inhibitor. How do you overcome a competitive inhibitor? You add more substrate. Oh, got it? So to overcome a competitive inhibitor, you add more substrate. That's what you do. Good. Okay. What about a non-competitive inhibitor? Well, a non-competitive inhibitor binds allosteric. Activation energy, the same thing. What does that even mean? You're not making anything, so there is no activation. That's even the thing. So in a non-competitive inhibitor, what's happening is you're binding allosteric. So this guy comes in here, binds allosterically. Allosteric is other than active. Allosteric, allosteric. KM and KCAT and all these terms that we're going to get to tonight have been on almost every single MCAT since the beginning of time. Allosteric means you bind to a site other than active, and you destroy the active when you bind. So where'd your active go? It went bye-bye, no active site. So you effectively remove the enzyme, okay? And then you have this thing called uncompetitive. So uncompetitive is not going to compete at all. What's an uncompetitive inhibitor? So we have non-competitive, we have competitive, and we have uncompetitive. Well, uncompetitive inhibitors, they bind while A and B are in the transition state. So when A and B are locked in this induced fit, this uncompetitive inhibitor locks them in here. And that's going to be interesting. Because one of the things you need to understand is that affinity is how well substrate bind an active site. So the uncompetitive inhibitor increases affinity like crazy because they're locked in the active site. So an uncompetitive inhibitor certainly increases affinity. And you'll learn right now that Km is inversely related to affinity. So if Km is inversely related to affinity, higher affinity means lower Km. Lower Km means, well, we're not going to release. We're just going to stay bound. Okay, so long story short, let's make a little chart. So we have competitive, we have non-competitive, and then we have uncompetitive. If you want to measure how an enzyme performs at low substrate, what is the measuring? Km, Km, Km. Km is the concentration of substrate at 1/2 Vmax. It's also simply the initial slope. So the initial slope of the enzyme graph is Km. You have a steep slope, you have a high Km. Initial slope, high Km, low affinity, something like that? No. If you have an initial slope that's really high, your Km is very low. If you have an initial slope that's very shallow, your Km, concentration of substrate at 1/2 Vmax, right, is very high. So look at this. Km of A, we'll call this enzyme A, we'll call this enzyme B. Which enzyme works better, A or B? I think you do know. It just depends on substrate. See, why are you all going with these weird answers? At high substrate, they work the same. They're getting the exact same. So at high substrate, they're getting the same because they have the same Vmax. And as I'm trying to get you to understand, Vmax is a measure when the substrate is high. But at low substrate, you can see clear as day that A works better. So low substrate, A works better. And low substrate, well, it took less substrate to get to 1/2 Vmax. It took less substrate to get to 1/2 Vmax, therefore it's more affinity, it has a higher affinity. So if you're lower your Km, the higher the affinity, the higher the initial slope. So Km is proportional to 1 over affinity. And that's proportional to 1 over slope. So if you have a very, very high slope, your Km is very low. And you have a high affinity, guys. That's kind of how we roll. I like it. Like the affinity. So. Okay, here we go. Competitive inhibitor competes for the active site, so of course it's going to take you more substrate to get 1/2 Vmax. So Km decreases because your affinity, your likelihood to bind your substrate is going down because there's somebody competing. Well, in a competitive inhibitor, what's going to happen to Vmax? Well, you can overcome a competitive inhibitor by making the substrate so high. No, this is not a line. We haven't even spoken about Lineweaver-Burke. This is just straight up concentration versus rate. This is an enzyme graph. So there's no change in Vmax because if you get substrate infinitely high enough, you can still get back to Vmax. A non-competitive inhibitor lowers Vmax because you're taking enzymes out of the picture. Where'd your enzymes go? They went bye-bye. But the enzymes that remain will still process low substrate just as well. That's why there's no change in Km. Think about it. If you took 50 enzymes away, who cares if I only have 3 substrates? So when substrate's very low, you don't need many enzymes. You need to match 1 to 1. Uncompetitive is very interesting. You ready to be very interested? Uncompetitive inhibitor, well, that is going to increase big time the affinity, because remember, uncompetitive inhibitor binds to the transition state. So here's A and B, and it just blocks these guys in. So your affinity is going to skyrocket, so your Km is going to be low. Low Km, high affinity. That's weird. And certainly you're going to lower Vmax because you're not going to be making any product. If you lock this thing into the transition state and you never make product, well, guess what? You never make product. All right, it's a nice little chart. You can better understand it, memorize it, or learn it. I hope you understand it more than memorize it. Be a better thing, don't you think? Yeah, hopefully don't memorize, understand. All right. Well, there's something called the Lineweaver-Burke plot. And there's a reason why Lineweaver and Burke got together and made this plot. I'm going to show you why. Okay, here's enzyme A, and here's enzyme B. Which one has a higher Vmax, A or B? Yeah, I'm not sure either. I don't know. We don't know. Nobody knows. I include me, because maybe B levels off. Maybe A levels off. Maybe they have the same. Maybe they have different. I don't know. So what? But who has a steeper initial slope, A or B? I know A has a steeper slope. So A has an initial slope that's steeper. So at low substrate, which one works better? Certainly A. But at high substrate, we don't know. And that's where Lineweaver-Burke comes in. Lineweaver-Burke says, let's take that rate and let's take that substrate and let's inverse and take the negative reciprocal. When you take the reciprocals of both axes and negate one of them, you get a linear transformation. That's how you do a linear transformation. That's like semi-log paper. Those guys, you guys don't know what semi-log paper is, you should. Semi-log paper, the purpose of semi-log paper is to take logarithmic functions and make it linear so it's easier to read. And that's what Lineweaver-Burke's going to do for us. So Lineweaver-Burke takes these guys and plots -1 over substrate versus 1 over rate. You get this. This point here, -1 over substrate is 0. That means substrate's infinity. And if substrate's infinity, that means that's your 1 over max. Yeah. Got it? The concentration of substrate at that point is infinity, because 1 over infinity is 0, and you're on the y-axis here, or the axis you were. Over here, we have -1 over Km. So if this is the normal enzyme, we're supposed to understand what the shift for a competitive, non-competitive, non-competitive inhibitor do in this instance. So let's try and understand that. Well, we know a competitive inhibitor changes Vmax or Km. I forget. A competitive inhibitor changes Km indeed. And if it changes Km indeed, then we're going to hold for the competitive inhibitor. We're going to hold Vmax constant, because you can overcome a competitive inhibitor by increasing the substrate. So what do? Well, I'll show you what we're going to do. We're going to change Km, and Km, does the affinity go up or down? Affinity goes down, so Km goes up. If Km goes up, you're getting closer to 0. -1 over a bigger number, closer to 0. So they're going to show you a normal enzyme, they're going to show you a bunch of graphs and say which one of the following is the correct Lineweaver-Burke transformation of a competitive inhibitor. And we just did it. A non-competitive inhibitor, well, what is that going to do? A non-competitive inhibitor will not change the Km. So our Km is going to be the same. But Vmax will certainly go down. 1 over a smaller number means a slope will flatten. These are weird words. The slope's got to increase. The slope has to increase. Why does the slope increase? The slope increases relative to the regular enzyme because 1 over the rate, 1 over the Vmax, your Vmax went down. Yeah, Vmax goes down, 1 over Vmax goes up. Got it? So there's your non-competitive inhibitor. Now all we got to do is our wonderful, handy, dandy little uncompetitive. So what is going to happen in an uncompetitive? Well, I'm going to tell you. What changes in uncompetitive? Uncompetitive Km goes way the hell up or down. Way the hell down. So Km goes down, therefore you move out this way. But it's an inhibitor, so Vmax should go down, and one over Vmax should go up. So is that the line we started with? No, we're going to change both of them. So long story short, in an uncompetitive inhibitor, as we know, the Km, or inverse to affinity, affinity goes up, Km goes down, Km goes down. Minus 1 over Km, well, it's a smaller number, we're going out further. And then Vmax certainly goes down, and Vmax goes down, we're going up on the graph, period, exclamation. So please understand the Lineweaver-Burke and the shifts, and we'll all get along just fine. I think that's pretty good. You'll be doing just fine. All right. It's not necessarily parallel. It can be parallel, but it doesn't have to be parallel. No, I mean, the Km can change more than the rate, or the Km can change less than the rate. Don't you think that's great? Yeah, mighty fine. Okay. Let us look at what happens. Well, we take some substrate, 3, 1, 2, 3, and we add an enzyme. And enzymes are catalysts, meaning they catalyze reactions, they speed them up. So enzymes speed up reaction. And when you do this, you get something called enzyme substrate. And the K going across here is K1. Enzyme substrate is the transition state. Anything that gets you to the transition state, is higher affinity. Anything that gets you to transition state is higher affinity. So K1, if you have a high affinity, low Km, K1 is going to be high. Got it? Then when you break apart and you become enzyme plus product, and you did your job, Mr. Enzyme, fantastical.
Love you.
We call this kitty cat. K-cat is the rate constant for the enzyme substrate dissociating to enzyme plus product. K-cat. And you need K-cat in order to make product, right? So that's going to be related to Vmax for sure. Well, going backwards, just because an enzyme binds doesn't mean it always does something. You might bind and release. And that bind and release is called dissociation. So you might bind and just dissociate, and that's called K2. Okay? So we have K1, K2, and K-cat. Well, what are we going to do about this? I'm going to teach you some things. I want you to know how to understand from these Ks what Km is, what K efficiency is, and what Kd is. Kd is pretty straightforward. Kd is the dissociation constant. Are you dissociating faster than you're actually forming or actually available? So if I want to dissociate, what number should be on top? Yeah, I agree. K2 better damn well be on top, and on the bottom is what? K1. No smoke and mirrors. This should be pretty straightforward. How about the next one? The next one we'll talk about is Km, and that's a little trickier. Km is inversely related to affinity. So do you want, if I have a low Km, I have a high affinity. So what numbers, if I have a low Km, so think about this, I have a high affinity. Low Km, high affinity. And what of these constants would help us realize a high affinity? In other words, get us to the transition state and keep us there. Because it's not about making product. That's not what affinity is. K1 for sure. Yeah, and what about K-cat? So if we want a high affinity and a low Km, we want K-cat to be on the numerator or denominator. Low Km, high affinity. Well, certainly K-cat and K2 should be on the same side of the division side. KCat and K2. Why would that be? Well, because they're going away from transition state, and certainly K1. So K1's the only thing that's getting us to transition state. And if you get us to transition state, that means we have a high affinity. So that's right. We want K1 in the denominator. So let's understand this a little bit. Point is this, and K2 is the same as K minus 1, those of you who didn't know that. Because we're going backwards, K2 is the same as K minus 1. Okay, so let's take a look at this. If KCat and K2 are high, that means that my affinity is low, my Km is large. Everybody understand that statement? If KCat and K2 are high, that means that I'm not binding it well, I'm releasing it back to its product, or its substrate form, or releasing it to something else. I don't care, but I'm releasing it. Got it? Good. Okay, so KCat and K2 are high. I'm going away from the transition state, and I have a low affinity, but my Km is high. So there's our second equation that I need you guys to be comfortable with. You got to be able to derive these or to deduce them or whatever you got to do. Get them done. Last but not least, and K efficiency is more of what you guys usually think Km is. K efficiency is, okay, if I have a really good binding, do I actually make product? So right away, I want who on top to make product? Yeah, I want KCat on top. KCat. So I want KCat on top. And on the bottom, I want Km. And let's decipher this. So if my Km is really small, then I have a really high affinity, and my K efficiency is high. So if my KCat is big and my Km is small, it's big number. Good. No, Km has multiple variables. So no, that's not true at all. You can't say, I mean, look, Km and KCat, that's only two of the variables. Got it? Yeah, the backwards, I mean, if it's forward is products over reactants, where backwards is reactants over products. That's fine. All right, so long story short, KCat is measuring how fast you go from the transition state to product. Right? How fast you go from transition state to product. Cool. All right. What is the difference between an apoenzyme and what else? An apoenzyme. Yeah, we can call this K minus 1. So they call them a lot of different things. So some books will call this K minus 1. Some will say that's K1, that's K2, that's K3. So this is K minus 1 right here. So we can call it K minus 1. That's more commonly, they'll call it K minus 1. Got it? So KD would be K minus 1 over K1. So if you want to call it K minus 1, that's fine. They call it anything they damn well want. Do you understand? What is the speed going from transition state to product? KCat. Yeah. KCat. KCat. No. KCat can't be 1 over Km because there's also other equations in there. There's other things going on here. It's not just K minus 1 over 1. Yeah. They don't cancel because K2 is K minus 1, right? Good. Okay. So, what is an apoenzyme versus a halo? What do you need? A coenzyme? Apo versus halo. Yeah, you need a cofactor. So an apoenzyme does nothing without its cofactor. And then we can make the halo enzyme. A lot of enzymes work like this, but not all. Not all enzymes have cofactors, so don't screw that up. Because they have asked that, and you guys hopefully know that. Now, cofactor, last I checked, comes in multiple flavors. Isn't it organic? Are cofactors organic? I think they can be. And that's our split. Organic, yes. Organic, no. What's an example of an inorganic cofactor? What's an example? Magnesium is a good example. What metals? Metals. Iron's a good example. Calcium's a good example. Very good. So magnesium is a cofactor for what enzymes? What enzyme? Kinases. Kinases use magnesium. Yeah, that's a thing. Kinases. What do kinases use? They use magnesium. You should know that. Got it? I like it. Okay. Organic cofactors are called coenzymes. Why don't you just call it an organic cofactor? Coenzymes. If it's organic, can this be a protein, this coenzyme? Yes or no? Can it be a protein? Can't be a protein. A cofactor is not a protein. So a coenzyme is an organic molecule that's a cofactor, but it can't be a protein, because if it was a protein, that would be quaternary structure. Got it? That would be quaternary structure. So if it's a protein, it would be quaternary structure, because multiple polypeptides needed to make an enzyme work would be quaternary structure. So coenzymes cannot be proteins. Please know that. Now you do. Okay. Coenzymes, of course, come in two flavors. Flavor Flav. Co-substrates and prosthetic groups. What's a prosthetic group? Cat, that doesn't make any sense. I hate to say it. Prosthetic groups are usually not vitamins. No, not necessarily. Yeah, they bind tightly. They bind very tightly. They bind irreversibly. Prosthetic groups bind irreversible. Got it? For the organic coenzyme not being a protein. Yeah, an organic coenzyme cannot be a protein. It can't be a protein, because if it's a protein and you stuck multiple proteins together, we don't call it that. It's just semantics, and we would call it a what? If it's multiple proteins stuck together, we would call it a quaternary structure. Because when you have multiple proteins stuck together to catalyze reactants, that's quaternary structure. That's not a coenzyme. Get it? Ooh, that's good. I feel like it's good. I feel good. Da-na-na-na-na-na. Co-substrates are your vitamins. So your vitamins tend to be co-substrates. Vitamin A for your eyes, a little retinol. Vitamin B's. So your co-substrate tend to be your vitamins. Vitamin B's are like niacin as in NAD, right? That's vitamin B. FAD as in a riboflavin. That's vitamin B. So these are all vitamin B's. TPP, thymidine, is vitamin B. CoA is vitamin B. Biotin is vitamin B. There's so many vitamin B's. Folate, vitamin B. All these guys are co-substrates, also coenzymes, also cofactors. So it goes up, all the way up. Get it? These are all. And then what about ADEK? These are not vitamin B's. What is ADEK? Vitamin A, D, E, K. The heme and hemoglobin is irreversible. That's why it's a prosthetic group. Yeah, ADEK are the fat-soluble vitamins. What's vitamin K do? That's a biggie, isn't it? Biggie. Vitamin K is a cofactor, isn't it, or no? Is vitamin K a cofactor? It's not thrombin. No. Is vitamin K a cofactor? It's a clotting factor. It's not a clotting factor. Wait, is vitamin K a clotting factor? Clotting factor and cofactor are very different things. A clotting factor is a protein that clots things in blood. So it'll clot blood. So does vitamin K clot blood? Yeah, good. It's involved in clotting. That's interesting. Vitamin K is needed for clotting. I'll go with that. So vitamin K is a cofactor to make the clotting factors. Got it? At least some of them. So vitamin K is a cofactor to make clotting factors. Clotting factors are proteins. It can't be, vitamin K can't be an enzyme. It's a co-substrate, and that's not allowed to be a full-fledged protein by the human definitions. I like it. I'm not gonna lie, I like it. You should know this chart. Apoenzymes, cofactors, been tested numerous times. Yeah, vitamin K is made by the netted flora. Yeah, that's true. So if you're on prolonged antibiotics, your vitamin K gets destroyed. And is that good or bad? That's bad because if you get a car accident, you're going to die. Well, I don't want to see that happen. All right, let's talk about more enzymes. More. If you have 6 different classifications according to IUPAC, what is the number 1 enzyme in your body? What is the number 1 enzyme in your body? I want to be your enzyme body. Kinase. Kinases, but what classification is a kinase? It's a transferase. Why is it considered a transferase? Because it's transferring a phosphate from ATP to a substrate in a process called SLP, substrate level phosphorylation. So a kinase takes a phosphate from ATP and transfers it to some substrate. We'll call this a substrate. It transfers phosphate. We'll make ATP. So kinase does this. This would be called a kinase. Got it? A kinase. Get it? It's called a kinase. You name it by the substrate in the direction ATP is phosphorylated. Got it? No, Mg+2 is not a coenzyme for a kinase. A coenzyme is a what? Organic molecule. Mg is not organic. Mg+2 is a cofactor. Got it? It's an inorganic cofactor, but it's not a coenzyme. Okay, so kinases transfer things. And your number 1, we have 6 IUPAC classifications. And yes, they'll be like, oh, which family does this belong to? Number 1 is transferases. You don't just transfer phosphates. There's lots of other transferases. You can transfer methyl groups. You can transfer acetyl groups, acetyltransferase. I mean, there's tons of transferases. But the one I need you to know is kinases. Transferase, that's number 1. Number 2, these are pretty straightforward. The isomerases. We isomerize things. So should you know glucose and fructose are isomers? Yeah, you should know. So glucose is 6-fructose to fructose 6-fructose. So all these are types of kinases. No, Kat, these are the 6 types of enzymes. There are 6 types of enzymes. And the first one we said was transferase. And a specific example of a transferase is a kinase. We have moved on from the kinase world. And we're going to talk about isomerases. It's all right. We'll clarify. Isomerases isomerize. Isomera warrior. So go from glucose 6-phosphate to glucose 6-phosphate. What kind of enzyme does it, and what's the name of it? By naming enzyme, it's not a mutase. Mutase moves phosphate. By naming enzymes, we look for commonality when it's bidirectional. Yeah. What? It's not glucose. How about hexosisomerase? We can do that. How about phosphohexoisomerase? Yeah. Well, no. How do you know fructose or glucose? Which one of these is the substrate? Glucose or fructose? I agree. It could be either. So what do you do in those cases? You find commonalities. And what's the commonality between glucose and fructose? It's a hexose. So you could call this phosphohexosisomerase. Got it? Isomerase. There's a specific isomerase called a mutase. And a mutase moves a what? A mutase moves a phosphate. So if I had some beautiful molecule like this, magenta, I had this beauty of a molecule, and here's my little lovely phosphate. And put an OH here and an OH there. And then I decided that I wanted to move my phosphate because I like to move it. And I moved my phosphate down to where? Let's move it to here. All right. What is the name of an enzyme that would do this. Well, there's no phosphate on the molecule, so we must have lost a phosphate. Exactly. It went away. So we removed the phosphate. This is called a phosphatase. So what did the phosphatase do? This is not a mutase. We didn't move it. That was a trick. Keep you guys sharp. What do? We moved it. So what happened? We made an inorganic phosphate. So what does that mean to you? No, a phosphatase is not a mutase. A mutase moves a phosphate, and it stays on the molecule. It just moves it. It stays on the molecule. There was no phosphate in the product. So what does that mean to you? Yeah. So what'd you do? Well, usually when you remove a phosphate, you have to use water to split it. We didn't make ATP. No, we did not make ATP. There's no ATP here. And if you use water to split this thing, then that should mean something to you. Yeah, this is a hydrolase. Hydrolases use water. That's the next one we're doing. So hydrolases use water. What does a hydrolase do? It uses water to split, like a phosphatase. So they don't always, but usually you do. So when you generate a free phosphate, it's called a phosphatase. Not to be confused with a phosphorylase, which adds a free phosphate. Got it? Okay, so let's try another example. Phosphatase is not a type of hydrolase, is true. Let's try another example because that was exhilarating. Let's say we had okay, what happened here? What happened here? You tell me what happened here. Hey, what happened here? What do you know? We moved phosphate. So this is a what? This is a mutase. Now, there's a double arrow. That means that nobody's really the substrate and nobody's really the product. So what are you going to do? You're going to look for a commonality. Show me a commonality. Show me the common. What's the commonality here? I agree. Phosphoglycerate. A carboxylate is a glycerate. So this is phospho because there's phosphate. You can't say 2 or 3 because it's on 2 and 1 and 3 and the other. Phosphoglycerate. Mutase. Nice. Let's go back to hydrolases for a minute. Hydrolase. What does a hydrolase use? It uses water to split things. You use water to split things. So classic hydrolases, of course, are all the digestive enzymes. And the classic ones we break are what? What are the classic we break? We break peptide bonds, we break glycosidic bonds, we break lipids up. Let's see how we do that. So let's look at this reaction. This is a reaction you should know. Yeah, you gotta really know this reaction. Come on, man. What's gonna happen? We're going to use water to split it. How do you know? Because the hydrolase is going to do this. Give me a hydrolase. Hey, give me a hydrolase that does this. Pepsin. Give me another one. Trypsin. Give me another one. Chymotrypsin. Give me another one. Carboxybenzamines. And last but not least, amino peptidase. So there are 5 proteases or peptidases in your body that you need to be aware. So everyone become aware, please. So what do they do? Well, each one of these, at least 3 of them, are very specific and will only do this and can only anchor to the peptide when there are specific R groups. And what they're going to do is exactly what I said. The enzyme overall is like here, and it's going to add water and attack the carbonyl, and it splits. That's it. That's what hydrolase does. You add water across the bond and you split it. Now, aminopeptidase and carboxypeptidase do it, but aminopeptidase does it at the amino terminus. And carboxypeptidase, you got it, does it at the carboxy. So, peptidases are one of our hydrolases. Let's do another hydrolase because this is so much fun. Another hydrolase would be for glycosidic bonds. Let's draw some rando glycosidic bonds. What kind of glycosidic bond am I making here? Have you got it yet? Wow, these are really bad answers. Wow. What the hell are y'all looking at? Yeah, Paige, I asked what kind of bond. What the hell? Okay, guys. Wow. Whoa. He's got like 20 answers and they were all bad. First of all, up is beta, down is alpha. Can we start with that? Yeah, glycosidic, but that's kind of cheesy. Or, yeah, of course it's glycosidic. All right, we should start with that. It is a glycosidic bond. So it's glycosidic, but I want what specific glycosidic bond. So up is beta, so we know it's an alpha, right? Can we go alpha? Yeah. Yeah. So it's an alpha bond. Now, I think I just wrote that. That's carbon 1 of Mr. Glucose over here, isn't it? Is that glucose? Down, up, down, up, down. Can I show what a beta bond will look like? Sure. Sure. What kind of bond is that? So is this glucose on the left, yes or no? Is that glucose on the left, yes or no? Looks like glucose. Walks like glucose. That's not glucose, folks. That's not glucose. Glucose, every chiral center has to flip. So if you go up, down, up, it would have to be down. Then it would be L-glucose. But if it goes down, so carbon 2, so here's carbon 1, here's carbon 2, here's carbon 3, here's carbon 4, here's carbon 5, and here's carbon 6. So this is a hexose indeed, this sugar. And it's an isomer. What's the only one that's screwed up is carbon 4. Yeah, this is called what? What's the carbon 4 isomer of glucose? It's galactose. And it is an epimer. This is an epimer of glucose, I agree. But nothing to do with what we're doing, because I didn't even ask that. Thank you for all the extra information. Very happy right now. Okay, I asked you what kind of bond it was. Got it? So the ups are what? No, it's good. There's an epimer. It is galactose. I want you to know all this stuff. So the bond between these two sugars is down. Does everybody see that? Okay. Now what do you want to do? How do we know this is not glucose? Because glucose goes up, down, up in terms of its hydroxys. Because glucose is the most stable sugar in your body and most abundant sugar in your body, and because it's the most stable because they all go equatorial. So bottom line is glucose has to go up, down, up, or it can go what? It is right, left, right, but that's in the open chain. Oh boy. You better get to biological molecules class. So glucose exists in 4 different isomers when it's in a ring. It can go up on carbon 2, down on carbon 3, up on carbon 4, and then down, up, down. The anomeric carbon, which is the most oxidized, can be up or down. That term is alpha and beta. Remember? That term is alpha and beta. Okay, that was fun. So we have galactose, and what's the other sugar? Folks, it's a furanose. This is a furanose. 5-membered ring is a furanose. This is fructose. So the linkage is carbon number what? Why don't we see? What else? Is this a hexose on the right? What the hell? Do you see the number 6? Okay, let me count again. 1, 2, 3, 4, 5, 6. Yeah, it's an alpha 1,2 linkage, guys. Does everybody see it's an alpha 1,2 linkage now, I hope? So that's an alpha 1,2 linkage. The dotted red would be a beta 1,2. It's carbon 2 on that fructose on the right. Is that alpha or beta fructose? Okie dokie. Well, why not count from the right on furanose, folks? Why wouldn't you count from the right on furanose? Somebody tell Sir Kenneth, why not count on the right for furanose? Somebody tell me what? Why not count on the right? Most oxidized carbon has to get the lowest number. Yeah. Most oxidized carbon has to get the lowest number. Most oxidized carbon is carbon 2 in this case. This beauty right here is the most oxidized, and he's got to get the lowest number. So if we start from the right, he gets 5. If we start from the left, he gets 2. I can see we got a little bit of work to do on this. Okay, long story short, it's an alpha 1,2 linkage. So I see a hole, I plug it. So say hello to glucose. Glucose is an aldose. Let's learn glucose because for some reason, you guys are not sticking with this well. Glucose likes to exist in open chain and also likes to exist in the ring. Do I put the hydroxy groups anywhere? Does it matter? I feel like it doesn't matter. Yeah, it really freaking matters. Where do you have to put the hydroxy to get glucose? Right, left, right, right. Right, left, right, right. Remember, right, left, right, 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 left, right, 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 left, right, right. If you put them any other way, you're not glucose. Right, left, right, right. You can say left, right, left, left, because that would be the other glucose. This carbon is the chiral center furthest from carbon 1, and we call this like the penultimate, like ultimate frisbee, but it's a penultimate carbon. So the penultimate carbon is the chiral center. The chiral center, I tell you, furthest from carbon 1, penultimate carbon. When the penultimate hydroxy is on the right, it is D. So this is D-glucose, better known as dextrose. T-glucose, better known as dextrose. Right, left, right, right. Well, you can flip all those chiral centers. When all chiral centers flip, what do we call this thing? It's a burn balls of my enemies. Enantiomers. So let's make the enantiomer. The enantiomer is still considered glucose. So in the enantiomer, it goes left, right, left, left. Left, right, left, left. And here you can see the penultimate hydroxy is on the left. This is L-glucose. Long story short, glucose has two configurations in the open chain, L and D. Got it? And right, left, right, right, or left, right, left, left. Okay, now, glucose really doesn't look like that. Glucose, because those are not 90-degree angles, right? Glucose looks like this. 1, 2, 3, 4, 5, 6. So if you notice, the hydroxy of carbon 5 is very much in the proximity of the aldehyde. And that lends to ring closure very nicely. Got it? That lends to the ring closure very nicely, doesn't it? And when you get ring closure of glucose, it looks a little something, something like this. The OHs, well, on carbon 1, was carbon 1 chiral, yes or no? Was carbon 1 chiral? Not yet, but it will be. When it undergoes ring closure, the anomeric carbon becomes chiral. Should you know that? Yeah. So the hydroxy group attacks, the electrons kick up, and we make this beautiful structure. And that OH can go up or down. Let's put it up for now. So that OH could have went up or it could have went down. If it went up, this would be a beta sugar. If it went down, it'd be an alpha sugar. Got it? How can you, is it still considered is it most oxidized? Is it still considered an anomeric carbon in the straight chain, folks? Yes or no? Yeah, yeah. The most oxidized. To know you're, oh, then that's where we're going next. So, for beta D-glucose, which is the most abundant sugar in your body, all are equatorial. All of your groups are equatorial. So I go OH equatorial up, equatorial down, equatorial up, equatorial down, equatorial up. And that is beta D-glucose. This is called a Hallworth projection, folks. A Hallworth projection looks like this. A Hallworth projection, you don't make your axial and equatorials pointing out. This is just a different way to draw this molecule. They make them pointing straight up and down. And they start with equatorial, 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 equatorial. And that's because in cyclohexane in the chair configuration, the equatorials switch up to down on every carbon. So instead of drawing out the chair, they just make this Hallworth projection. Axial down, axial up, axial down, axial up, axial down. Got it? Okay, here's the deal. If beta D-glucose is the most abundant sugar in the universe, then no, you're not going to start with axial up. No. This is a Hallworth projection. Go talk to Dr. Hallworth. So we go equatorial up, equatorial down, equatorial up, equatorial down, equatorial up. So that's beta D-glucose. Got it? Well, what would beta L look like? What would beta L look like? Well, they're not all axial because that means that carbon 1 is still beta, which means it's equatorial. Beta is equatorial. Alpha is axial. So what would beta L look like? Well, D and L all switched. Beta means the anomeric is up and it's equatorial. But now, instead of going down equatorial, we're going to go up axial, down axial, up axial, down axial. And here's our beta L-glucose. So again, knowing the Hallworth, that it goes up, down, up, down, up, down for equatorials, and it goes down, up, down, up, down, up for axials. And obviously, the equatorial is more stable, but that doesn't mean that's the only thing that exists. All these sugars exist. All right, so how would you know? So let's hopefully bring this home. So if I've got sugar, and it looks like this, and let's say I had an OH here, an OH there, here an OH there, an OH everywhere, an OH, and I said, hey, what are all these substituents? I would hope that you know beta D glucose is up, down, up, down, up, down, up, down. Got it? Up, down, up, down, up, down. I would hope you know beta D glucose is that. So first things first, what can you tell me about this sugar? You're supposed to tell me everything I want to know about the sugar. You want to tell me anything? Please do. You can tell me something. It's a stereoisomer of what? Everybody's a stereoisomer. That doesn't make any sense. It's not glucose. Yeah. Okay. All right. Okay, first things first. How about it's a hexose? How about it's an aldose? It's an aldehyde. What functional group is here? What functional group is here? Because epimers are open chain. That's called a it's a HOCOR. It's not a ketal. HOCOR. It's a hemiacetal. You got to be able to recognize hemiacetals very well for this test. Carbon attached to a hydrogen to an OH. Now you got your HOCOR. HOCOR. Say hello to my little HOCOR. So this sugar, so they're going to show you the sugar and say, oh, which applies. And it's going to be a Roman numeral type question. Get it? That's the thing. So what applies? It's a hexose, it's an aldose, it's a hemiketal. Is it a pyranose or a furanose? It's pyranose. Furanose would be a 5-member ring with an O. It's heterocyclic. That's kind of cool. I don't know if it's cool, but it is. It's heterocyclic. Is that cool? That's pretty cool. Heterocyclic means not the same atom. So there's multiple atoms in this bad boy. Is there more? Yeah, there's more. Okay, now, if axial is down, then axial is up, then axial is down, that means that's equatorial. If that's equatorial up, equatorial would be down, that's axial. If that's axial up, axial would be down, that's equatorial. What? So you got to be able to identify that. Again, it's all based on one molecule, and that molecule is beta D glucose. Beta means up. Beta, equatorial. D glucose, they're all equatorial. So it goes up, down, up, down, up. And now everybody's equatorial, guys. Okay? Yeah, beta's always up, right? Okay, so let's try another one because that was mildly interesting. What's the last bullet? Heterocyclic. Heterocyclic means more than one atom. You're welcome. Okie dokie. Oh boy. Hello, H. Hello, Scotty. Hello, 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 hello. Hello. Ya da 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 da. What kind of sugar? Quicker, quicker, quicker. Let's get this down. I got a lot I want to cover still. What kind of sugar? Sugar. It's a hexose. Okay. It's a 6-membered sugar. Hexose. What else? It's pyranose. I agree with that. It's not a furanose. Furanose 5-member ring. There's a hemiacetal there. Hemiacetal. I agree. It's heterocyclic. That's the thing. Heterocyclic. It is an aldose. If you wait a minute, it'll be an aldose. You'll see why. It is an aldose. Heterocyclic. So this is the beta anomer, huh? So it goes equatorial up, equatorial down, but that's up. So that's axial. Axial up, axial down, axial up. And then if that axial is supposed to be down, that's equatorial. So what is this in relation? I wonder if does this have any relations to glucose? Yes. Does this have any relation to glucose? Yes. To which glucose is this most related to? Good question, Scott. No. To which is C5 is down on C5 always axial and yes. So which glucose is this related to? I feel like we're related to beta L is correct. Yes. If I change that right there, I like the way you do it right there. If I change that carbon 5, I will be beta L glucose. This is beta L glucose? No. This is the C5 epimer of beta L glucose. An epimer is a diastereomer where only one chiral center flipped. So C5 epimer beta L glucose. I hope we're getting somewhere. Okay, now, what happens with these anomeric groups? They're very unstable. Glucose pops in and out of the linear chain in a heartbeat. Got it? So what's going to end up happening is these electrons can kick down and these electrons can kick over. So if I kick those electrons down, boom, and I kick these over, what do I make at this point in time in your life? What did I just make? When I did this, I made what? I made an aldehyde. I made the open chain. I made an open chain aldehyde. Can we say that? Yeah, we can. I made an open chain aldehyde. So what was the aldehyde test? You guys remember? Tollens, the silver myrrh. So your Tollens positive. That thing's Tollens positive because it really is an aldehyde. You just got to wait a couple seconds because it's spontaneously doing this. Now, I made the aldehyde. What carbon becomes the aldehyde? What carbon becomes the aldehyde? No, 6 is way the hell over here. What? Yeah, 1 becomes it. 1. That's carbon 1. Carbon 1 becomes the aldehyde. Got it? So carbon 1 becomes the aldehyde. And then the rest of these guys. So this will be interesting. This will be a good test for you guys. Where do we put our OHs for this? So I want to transform this to a linear. I want to transfer this to open chain. Where do you put your OHs? Does it matter? Yeah, of course it matters. Where do you want to put your OHs? How's it go? Right, left, right, right? No, it's sure as hell not glucose. Right, left, right. No. Left, right, left, left. Wow. Okay, let's start with the first OH. Does that go on the right or left? Let's look a little better. Learn. Okay, this OH is going to be the carbonyl. It doesn't go anywhere. You lose a chiral center. You understand? You lose a chiral center. If somebody says, hey, how many chiral centers does glucose have? You're supposed to say what? 4 or 5. Which one? How many chiral centers does glucose have? What are you supposed to say? You're supposed to say 4 or 5. And then you're supposed to say yes. Correct. Glucose has 4 chiral centers when it's in an open chain and 5 chiral centers when it's in the ring. And the new chiral center that forms is the anomeric. Got it? Good. Okay, so when this OH kicks down and you make the aldehyde, I asked you, I circled that red OH and I said, where'd that OH go? Equatorial axial. And the correct answer was neither, because the carbonyl it makes is a chiral. Whose OH is that right there? Whose OH is that? Whose OH is it anyway? It's carbon 5's OH. It's the penultimate OH. Okay, let's take it step by step. Axial, if we remember, glucose is right, left, right, right, and they're all equatorial. Right, left, right, right, and they're all equatorial. So where's axial? So write it. In a 6-membered sugar, it goes right, left, right, right, and they'll be all equatorial. And that's 2, 3, 4, 5. I mean, that's a memorize, guys. You got to know that D-glucose is the most abundant sugar in our body. Dextrose. That's what we hang. You never heard of hanging dextrose? Yeah. Okay, so carbon 2 is axial. So where do you want to put it, on the right or left? Oh my God, up is right. What does that even mean? You want to put it on the left. Do you understand? Carbon 3, right, left, right, 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 left, right, right. Carbon 3 is axial. So where do you want to put it? Put it on the right. Now you're getting the hang of this. Feel like you're getting this. Feel like you're feeling pretty good at this. Yes, they've asked you to convert the linear. Carbon 4 is axial. Like carbon 4, when it was equatorial, it was on the right, so therefore it's on the left, right? Or left, right, left. 1, 2, 3, 4. Carbon 4 is on the left. Carbon 5, where is it? Carbon 5 should have it on the left. Why is it on the left? Carbon 5's equatorial should be on the right. That looks good. Left, right, left, right. Left, right, left, right. Get it? We're going to do another one because that was mildly painful and disturbing. Okay, so when they ask you something like this and they show you a beautiful molecule and it looks like this. Hello, beautiful molecule. Hello, Scotty. How you doing? Okay. First things first, what kind of sugar is it? Quicker. What can you tell me? Oh, it's pyranose. Oh, it's hexose. Oh, it's a hemiacetal. I hope that's all old hat. But now I want to know what this looks like in the open chain. So in the open chain, we go boom, and we break this bond. You understand? What kind of bond do we break to have this hemiacetal go into the open chain? The answer is hemiacetal. Got it? So we break a hemiacetal. Everybody see a hemiacetal? HOCOR. We break the hemiacetal. And what do we do with that? We make it into an aldehyde. Not formaldehyde. No, not formaldehyde. I know. Jim wrote formaldehyde, as in like we form aldehyde. Get it? Get it? Come on, man. That's not bad. All right, here we go. Jim, no, back me on this. We form aldehyde. I said, come on. Where are you putting your OH? Show me what? Show me what you got. Show me what you made of. I got one going left, right, right, right. Left, right, right, right. Anybody else? Well, I got another left, right, right, right. Okay, let's do it. Axial down, axial up, axial down, axial up. Wait, that's equatorial. Equatorial down, equatorial up. I like it. And then you remember handy dandy little glucose decoder key. Right, left, right, right. Equatorial, 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 equatorial. Ever seen it? 2, 3, 4, 5. 2, 3, 4, 5. Keeps the diaphragm alive. So if these are all equatorial, which they are, so the right is equatorial on 2, but we are on 2. We're axial. So we're on the left. On 3, we're axial. We should be left if we're equatorial, but we're on the right. 4, we're equatorial. That's where we're supposed to be. That's over here. And 5, we're equatorial. So beauty. Left, right, right, right. Okay, do we understand how to switch between open and closed? Yes or no? Close and open, penultimate attacks the anomeric, and we closed it. Electrons kick up, we make a new chiral center. So you should be insanely adequate at switching between open chain and your cycle molecule. Well. When you come back after you do this, it's possible that this guy, because he's a carbonyl, you would think when you attack a carbonyl that it's going to be 50-50, right? When you attack a carbonyl, is it 50-50 adding to the top and bottom? It's not, is correct. Why is it not 50-50? Holy shit, we're doing hydrolases. I forgot what we were doing. That's good. It's not 50-50. Why is carbon 4 equatorial? Because it goes axial down, axial up, axial down, axial up. So the hydrogen's axial. Therefore, it's equatorial. It's definitely not 60-40 because when the OH adds, so like when this hydroxy group comes in here and this OH, so that carbonyl can go up or down because it was trigonal planar, but it's not 50-50. And the reason it's not 50-50 is because this whole thing adopts the cyclohexane configuration and there's an equatorial. So it's much more like 90-10. So 90% of the time it's going to go equatorial, 10% of the time it'll go axial. So, but it is possible when you do this and it reforms that this guy switches to up. So when beta D-glucose spontaneously goes back to D-glucose, is D-glucose a pyranose, yes or no? No, it's the open chain. There's no beta. If you have a beta or alpha, you're in a closed chain. So no, D-glucose is open. This is the open chain. Got it? And then it's possible that the OH now kicks up and you make alpha. Because, and is it likely? No, more than likely it's going to go back this way. But it's certainly possible you go to alpha. So long story short, these are isomers. Yeah, this is an isomer. And they're called what kind of isomers? Some but not all flip, so they're diastereomers. But they're specific diastereomers called what? They're specific diastereomers called epimers. And they're specific epimers called anomers. And of course, lo and behold, they got to give an anomeric, when you switch from one anomer to another anomer, they got to give it a name. And the name is whacked. Mutorotation. So mutorotation, the product versus reactants in mutorotation are anomers, epimers, diastereomers, isomers, same thing, but not really. So anomers most specific. So somebody asked a moment ago, why don't epimers switch? Because epimers don't get attacked. The anomers are switching because they're getting attacked and reforming. And they have this carbonyl that can go up or down. Got it? I like it. I like it. So anomers spontaneously switch back and forth. And glucose is constantly doing this. It's like I'm in the open, I'm closed, I'm open, I'm closed, I'm open, I'm closed, and it's keep going on and on. Obviously, the majority of the time, it's in the ring. It's very, very, very less reactive in the ring. It's much more reactive in the open chain. Got it? So if you wait a second, it'll switch. Wait another second, it'll switch. All right, I feel a little bit better about glucose. Now, how do we make a glycosidic linkage? This is where we got in trouble with these hydrolases. Well, we form most of our biological molecules via dehydration synthesis, right? So we're going to lose water. So we take these two beauties here. Ready for these beauties? Do 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 do. Okay, who's on the left? Who's on the left? Who's on the left? Who's on the left? On the left, on the left. Who's on the left? Who's on the left? Beta D, baby! Yeah, yeah, yeah. This is beta D glucose. Yeah, of course it's a pyranose. This is beta D glucose. Who's on the right? Who's on the right? Ooh. Alpha or beta, Miss Allie? Fructose, I agree. Alpha or beta? Let's try this. Is that OH equatorial or axial? Is that OH equatorial? It's neither. It's neither. There is no equatorial and axial when you're in a 5-member ring. So there's no equatorial and axial here, guys. Yeah, sorry they test that. But these methoxys look a little crowded to me. So who do you think is more stable, alpha or beta, based on what I've been teaching y'all? Who's more stable, alpha or beta? Beta's more stable. So do you think it'd be a more stable molecule if we put those methoxys in trans to each other? Yeah. So is this alpha or beta fructose? Well, according to 2 summers ago in July, it is indeed alpha fructose. Is that a thing? Yeah, they tested it. Okay, now, yes, this is alpha fructose. Okay, let's make a linkage. So we're going to attack one of the anomeric. Wait, how is alpha if no axial equatorial? Because it's how the convention goes. The more stable is beta. It's a different convention for glucose versus fructose. Oh my God, I never learned that. This can't be true. Okie dokie. So, how do we do it? Who's attacking whom? Is fructose attacking glucose or glucose attacking fructose, or doesn't it matter? Maybe it doesn't matter. Glucose attacking fructose or fructose attacking glucose. What does it matter? Who's attacking whom? From sea to shining sea. Fructose to glucose. Why, Miss Alexandra? Why does that have to be? It doesn't have to be that way. It doesn't have to be this way. Who's it gotta be? It's only, oh my God, it has nothing to do with stability. No. Okay. Either way. Allie's like, yeah, I'll do it either way. No, Miss Allie, it's not right. Okay. So what they've done is they've drawn this picture and they've shown the glycosidic linkage between them. And they said, whose O is it anyway? And one of the answers was literally, it doesn't matter. It could be either. That's definitely not right. That's never right. When is that right? Never. Got it? That's never right. But seriously, was that right? Never. Okay, that's not right, which it's not. What do you want to tell me? You want to tell me more? Tell me more. Tell me more. Like which one is most oxidized? The most oxidized carbon is going to get attacked. The most oxidized carbon is going to get attacked. So this carbon has 2 O's, folks, and oxygen sucks electron density. It oxidizes it. Get it? So obviously it's what? More or less oxidized. But wait. This carbon over here has 2 O's. Looky here. So based on the oxygens, we're equally oxidized. Does everybody understand that? Those are both the anomeric carbons, respectively. Don't forget, carbon 2 in fructose is the anomeric. Don't forget, carbon 1 in glucose is the anomeric. Got it? Well, if all this is true, which I'm pretty sure it is, then so are they equally oxidized? And maybe it doesn't matter. No. Well, what happens is R groups, as in carbons, push electron density. So the R groups push electron density. And when they do, they make this less positive, less susceptible to nucleophilic attack. So here you have 2 R groups. So long story short, really wasn't that long of a story. Which carbon is more oxidized? Carbon 1 of glucose or carbon 2 of fructose? B, glucose. Yeah, glucose. Glucose is more oxidized because it only has 1 R group to reduce it, whereas fructose has the 2 R groups to reduce it. So in actuality, that carbon's more stable in fructose than it is in glucose. Got it? Long story short, who's attacking whom? The OH from C1 of fructose is going to attack, and then water is going to leave. That's called dehydration synthesis. And you're going to end up forming a bond that looks like this going down. And this is where we came into the picture. This is an alpha 1, 2. Got it? So this is an alpha 1, 2. How do you know the glucose is D? Is that an equatorial or axial position? Is that methoxy equatorial or axial? Abby, you asked the question. Abby fell asleep. She asked the question and went right to sleep. It's equatorial. And if it's equatorial, that means right, left, right, right. Got it? Oh, you're there. Right, left, right, right. So if right, left, right is equatorial, then if it's on the right, it's a D. Got it? Oh, so you say, oh, or no. Good, good, good. All right, moving on. So, holy cow. Enzymes. Oh, there we go. We had, let us review. We had our isomerases. And one of the isomerases was a mutase. Is right, left, right, right only for D? No, right, left, right, right is only for D-glucose. It's not for D, it's for D-glucose. Isomerase, there was a mutase. So the O from before was fructose's O. Yes. Yes. Whose O is it anyway? It was fructose's O. And it was fructose's O because the carbon of glucose was more oxidized. Got it? No, C2 from fructose. The hydroxy from C2 from fructose. The hydroxy from C2 from fructose attacked carbon 1's anomeric. I said the anomeric from fructose. The anomeric doesn't have to be C1. In this case, it's C2, right? We got 1, 2, 3, 4, 5, 6. So the anomeric for fructose is C2. You should probably know that. Maybe. Yeah, we're forming sucrose, alpha 1, 2. Alpha 1, 2 is sucrose and D and table sugar. Interestingly enough, about sucrose is when it forms. So here we go. We just formed this beautiful linkage together. Whose O was it anyway? Whose O was that? Fructose, 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 fructose. If you better damn well write that down and be like, I'm supposed to know why that's fructose's O. What? If you don't get it, well, then be like, what? Not what. Got it? Good. What? So that is fructose's O. That's the first thing. Second thing is what functional group resulted when glucose and fructose linked? That's definitely not an ether. But that didn't happen. It's definitely not an ester. An ester is a C double O to an O. Glycosidic not a functional group. That's the name of the bond. Hemiketal is dead wrong. Hemiketal. Fructose is already a hemiketal. Oh, core. Acetyl. I don't even know what that means. Oh, you're trying to say acetal, Jackie. That's what you're saying. Acetal. Rocor. Rocor. Acetal. Got it. Acetyl and acetal are very different things. Please know an acetyl group is just a methyl with a carbonyl, right? We acetylate things. That's called an acetyl group. An acetal. Good. Okay, so I asked you very nicely. I was very polite about it. What forms when glucose and fructose link? Well, and you should know sucrose forms. So this is sucrose. And you should know the bond between them is an alpha 1, 2. And the 1 is from glucose and the 2 is from fructose because they're both anomerics. Well, let me ask a question real quick because I'm a little confused about things. Where is the anomeric hydroxy group in this molecule? Where is it? On which carbon? They're gone. There's no anomeric hydroxy group. And as such, since there's no anomeric hydroxy group, we call this a what? Non-reducing sugar. A non-reducing sugar has no anomeric hydroxy. Got it? We got rid of them all. We used, when the two anomeric carbons react with each other, you're going to get a non-reducing sugar. When the two anomeric carbons of any sugars react with each other, you're going to get a non-reducing sugar. Is it possible to have two glucoses link and make it a non-reducing sugar? Yes or no? Is it possible? No, it's not stuck. It just means it can't be reduced. No. Does it? What's the linkage? For two glucoses linked together, what is it? Marshmallows. Where are you guys getting this shit? Oh my god. No, 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 no. Oh my god. Wait. What the hell? Okay. Yeah, Jackie's got it. I agree. That's a good one. Okay. So you guys were saying some crazy stuff. You're saying this. So this would be a what linkage? Here's 4, here's 1. This would be an alpha 1,4. Does everybody understand that? So if that's an alpha 1,4, is this sugar reducing or non-reducing? Which is, of course, what? This is maltose. Is this reducing or non-reducing? It's a reducing sugar. So why y'all saying that? I asked you, how do you link two glucoses and get a non-reducing sugar? And a bunch of y'all were telling me alpha 1,4s. That makes no sense. Alpha 1,6 makes equally nonsense. Alpha 1,1 makes the total sense. It's just, basically you're getting rid of, that's called trehalose. You don't have to know that, but you have to understand that when you link an alpha 1,1, what happened? Your anomeric hydroxys went bye-bye. So an alpha 1,1 or a beta 1,1 of glucose, could be D or L, is what? Yeah, got it. I don't know about the ring flip. This has nothing to do with ring flip. So, nothing to do. They just joined up differently. That's not ring flip. Ring flip is different, right? Okay, long story short, and that's that. If you want two glucoses to make a non-reducing sugar, you can do alpha 1,1, you can do beta 1,1, and you can do D's or L's. So there's 4 possible, more than 4 ways, right? Because you can do DD. So how many? That's a pretty cool question. How many sugars? How many disaccharides made up of glucose are non-reducing? How many disaccharides made up of glucose are non-reducing? Alpha, beta, beta, alpha. Whatever you want to call it. Whoever's up, whoever's down. No, not 1, Zach. I already drew 2. How many? I believe the answer is lots. Let's do it. So how many? Hopefully we'll get this now. So I could take glucose and do what? I could do down, down. Yes. I could do up, up. Yes. But why can't I do down and up? I can, thank you. Everybody getting the idea? So I can do down, down, up, up. What would this linkage be called that I'm drawing horrifically? What would this linkage be called? This would be alpha 1,1. This would be beta 1,1. What's this one? Well, this guy's going down, so he's alpha 1, and this guy's going up, so he's beta 1. Got it? This is not maltose. This is 1,1. Maltose is 1,4. Oh, alpha 1, beta 1, beta 1, alpha 1. Now, alpha 1, beta 1, and beta 1, alpha 1 are the same thing because you can't distinguish between the glucoses, right? So it would be the same thing because if you just turn this around. So alpha 1, beta 1 is the same thing as beta 1, alpha 1. It has to be the same because they're both glucose. What about 1,6? Oh my God. Naz, 1,6? If you link 1,6, the carbon 6 hydroxy, you still, on that molecule, you still have an OH on carbon 1, so it would be reducing. Got it? Okay, so I asked the question, I still haven't gotten the answer. Yeah, it's beta 1,2. It's not sucrose. Beta 1,2 sugar is not sucrose. It's called something else. Okay, so now let's try it again. Everybody understand what I'm trying? I'm trying to make a glycosidic bond, which is a bond with sugar, between glucose on carbon 1 and glucose on carbon 1. And I said, how many ways can I do it? I'm getting some strange answers. Well, what about DNL glucoses? No, it's not 3, because what about DNL? So I could have D to D. If I have D to D, there's 1, 2, 3. What about D to L? There's 1, 2, 3. What about L to L? There's 1, 2, 3. What about L to D? Well, that wouldn't work. L to D would be the same as D to L because they're both glucoses. Everybody's starting to feel the hang of this. So what's the answer to this miserable question? Yeah, I agree. The answer is 9, folks. 9. There are 9 possible ways. There's so many ways to link glucoses. That's why a lot of researchers thought that sugars were the genetic code, because there's way more ways to store information in sugars than there is in DNA. Way more. DNA, you got 3 nucleotides, 64. So I mean, 4 nucleotides, and you can do what? You have a codon that's 3 things, so you got 64 possible codons. Man, here you could link all these different things and make them different signals. Yeah, happy thoughts. Okay, let's get back and bang out these enzymes real quick, please. We've got transferases, like kinases, specific thing. We've got isomerases. We've got, what else? What did we do? We did transferases, we did isomerases, we did hydrolases. They use water to split things. And that gave us on our little glucose rant, which is good. It was a good rant. I had fun with it. We've also got, so that's 3 of them. We got ligases, like DNA ligase. Yeah, ligases put things together. So when you have A plus B goes to C, you say you ligated it. Ligase, and the specific ligases, it was a good rabbit hole. The specific ligases are, what are specific ligases? There's synthases and synthetases. Synthetases use the ATP. Yeah, synthetases. Who comes up with these names? Synthetases use the ATP. Synthases, synthetases. Got it? Or ligases. Then you have lyases. Lyases break things apart without water. Because if you split with water, you're a hydrolase. Split without water. Split without water. Last one that we're going to spend a little bit of time on. Oxidoreductase. So there has to be a redox. How do you tell if something's a redox? How do you tell it? How do you tell it? How do you tell? Change an oxidation number, change an oxidation number, change an oxidation number. I feel like it's change an oxidation number. Good job. Change an oxidation number. A lot of y'all think that. Good. That's good for you. Okay, so if you see charges appear, then is it an oxidoreductase? I don't know. Is this an oxidoreductase reaction? Yes or no? Yes or no? Did you check the oxidation numbers before you gave me that horrible answer? No, I didn't think so. Ay, ay, ay. Ay, ay, ay. Ay, ay, ay. Well, what happens here? They're all keeping their same, folks. The oxidation number stayed the same, meaning what? Meaning it is not an oxidoreductase. This is not an oxidoreductase. Got it? Should know it. Is it an oxidoreductase? No. I don't think so. I feel like it's not. You do. I don't have a problem with that. Okay. The classic oxidoreductases utilize beautiful vitamins. NAD, niacin, NADP, niacin with a phosphate, FAD, riboflavin. They're going to utilize these as cofactors, these coenzymes. And any oxidoreductase that utilizes NAD, NADP, or FAD is called a what? It's called a dehydrogenase. So specific oxidoreductases are dehydrogenases. So NAD plus likes to do what? Reduce or oxidize. Well, it likes to get reduced, so it's the oxidizing agent. Agreed? So NAD plus will oxidize. Is that a thing? Yeah, it's kind of a thing. So if I had this and I added NAD plus, what would you name the enzyme? Como se llama? What would you name the enzyme? The full name of the enzyme, please. Enzymes are named substrate and what it does. So this is called butanol. Yeah, dehydrogenase. Nice. Butanol dehydrogenase. They're going to ask that? Yeah, they're going to show reactants and they're going to ask you what's the name of this enzyme. They do that all the time. When do they do that? All the time. Got it? So dehydrogenase, classic. FAD oxidizes and makes what? It likes to make double bonds. So when you oxidize a alkene of sorts, you're going to make a double bond. All right. So where do we make the double bond in this beauty? This 4-carbon beauty? Well, we're going to make it where? So we're going to oxidize because the FAD plus gets reduced between 2 and 3. And what's that? Is there a name for that? That sucks. That succinate dehydrogenase. And what'd you make? Or butadioic acid dehydrogenase. That's the I effect. What'd you make? You made fumarate. This is in the Krebs cycle, right? You made fumarate. That succinate. So should you recognize some of these structures? All of them. Every one of these structures. If you don't know them, start putting them on note cards. That's succinate, and we use an FAD, so we did a dehydrogenase. Let's try it again, because that was exhilarating. If you had, let's say, a carboxylic acid, let's say we had an acetyl group and a carboxylic acid. Is that legal? I think it's legal. Most states. So if you had an acetyl group, carbonyl with a methyl, and a carboxylic acid, and you were so inclined to do something with that, let's say we do this to it. No, you won't do that. Well, name the enzyme. This is a classic. It's a classic, I tell you. Como se llama, Mr. Enzyme? Mr. Enzyme, wait for me. Got a letter to see. First of all, that sure as hell not acetic acid. That's pyruvate. That's a pyruvate. So what do you got to do to pyruvate? We reduced NAD, so we do what? We oxidize NADH, so we got to do what? We got to reduce this bad boy. So what you're going to do is make this beauty. And this guy is lactic acid. So this is lactic acid. So we just lactated, different lactate. So lactic acid. So what's the enzyme, folks? Anytime you use NADFAD, it's not pyruvate dehydrogenase because dehydrogenases are named in the direction that NAD plus is used. It's named in the direction that NAD plus is used. So it's called lactic acid dehydrogenase. Is this fermentation or not? This fermentation? No. Yeah, the 11-step program. This is the 11th step of fermentation. You should know this. What step is fermentation? This is 11th step. This is the 11th step of fermentation. What's the 11th step of fermentation? Here it is. There it is. Just because we can. How many NAD pluses per glucose? Per glucose, how many NAD pluses does fermentation yield? So you should know per glucose we make 2 pyruvates. I know we haven't done all this. Per glucose, Shen. Per glucose. Ay, 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 ay. How many ATP does fermentation make? What page? Then why the hell do you do it? You do fermentation to get your 2 piddly ATP as opposed to 36. So you make 2 ATP in fermentation. Are we clear? Because most of y'all, for some reason, never learn that fermentation has 11 steps. Step 1 through 10 is glycolysis, glycolysis. Step 11 is right here. So, long story short, fermentation is an 11-step program. And the goal, living the dream, is to regenerate one of the reactants of glycolysis. To regenerate one of the reactants of glycolysis, we need this last step. Regenerate implies, outrightly states that you use 2. If you use 2 and you get 2, then how many did you get? None. So you get 0 NAD plus from fermentation, guys. That's a classic. This is Biochem. Welcome to Biochem. All right, that's enzymes, folks. That's not bad. Okay, let's bang out G proteins real quick. G proteins are fun. You guys ready to have some real fun? First of all, they want you to know for some absurd, insane reason that G proteins are 7 transmembrane alpha helixes. So please know that. They've tested this a million times. I know of at least 10 MCATs that have had that question, where G protein is a 7 transmembrane alpha helix. 7 transmembrane alpha helix. You should know the alpha helix has how many amino acids per turn? 3.6 amino acids per turn. Should you know that? Yeah, they've tested that on the last test, allegedly. You should also know that in nature, it's mostly right turns. And last but not least, you should know the most common amino acids in an alpha helix. One of the most common. There's your Malec. 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 M-methionine, A-alanine, L-is leucine, E is epinephrine. No, glutamate. And K, I likes you, lysine. There are no, in an alpha helix, there are no prolines and glycines. If you see proline and glycine, so what they're going to show you a long stretch, and they're going to put the single letter abbreviations. They're going to show you a long stretch of peptide. They say, where's the most likely place there's an alpha helix? And you're going to find the Malix without the pro. It doesn't have to be that order either, by the way. It's just a bunch of M-A-L-E-Ks. Got it? Good. Malec. Malec are the amino acids of an alpha helix. Okay, anyway, G protein, 7 alpha helix, transmembrane protein. I feel like that's a thing. What do G proteins do? G proteins are peptides, so we're going to bind extracellular. And G proteins are trimeric, meaning that there are 3 subunits intracellular with the Rougy. And the three subunits are, and they're all in the membrane, guys, are G beta, G gamma, and G alpha. So those are our three all G proteins are trimeric, three proteins. They're called G proteins because the glue that holds them together is GDP. But when the ligand binds to the receptor, could be a hormone, could be a bunch of things. GTP replaces GDP. And these guys split up. And when they split up, what happens? We get G beta and G gamma floating away. That's good because they were inhibiting G alpha. So G beta and G gamma, peace out. Got it? They're going to cruise away. And then G alpha over here, with its newly found friend, GTP, goes to work. So the workhorse of G proteins is G alpha GTP. Now, there's three G proteins you should know, of course. And you should know GS, which is stimulatory, GI, which is inhibitory, and you should know GQ, which is just GQ. So we're going to do GS first, but they all start this way. Are we clear? So they all start this way. So that being said, I'm going to cut and paste this and use it on the next line because they all start this way. G alpha is going to stimulate adenylate cyclase. So GS is all about the A's. We're going to activate adenylate cyclase. Adenylate cyclase will convert ATP, and this happens in the membrane, to CAMP. CAMP, being the secondary messenger he is, he's going to leave the membrane, right? This is still the membrane. This whole thing is membrane. CAMP's going to leave, and CAMP's going to find whom? Inactive protein kinase A. So we're going to find inactive protein kinase A. We're going to activate it. CAMP activates it too, protein kinase A. So in the end, what do we get? Activated protein kinase A. They can go phosphorylate a bunch of things. So GS is all about the A's. Adenylate cyclase. Is G protein in the membrane or only the receptor? Oh no, the whole G protein's in the membrane. This line represents the plasma membrane. So everything's occurring in the plasma membrane except CAMP. CAMP's the first structure to leave the plasma membrane. Got it? Good. Okay, so GS, we've got adenylate cyclase. We've got increased CAMP. Then we got increased protein kinase. Yes, that's GS. GI is really easy. GI is inhibitory, so there's some ligand that binds, and then all of a sudden you go through the exact same process, but this time the G alpha with the GTP on its back inhibits adenylate cyclase. So for GI, we're going to, here we activate adenylate cyclase. Yeah. And for GI, we inhibit adenylate cyclase, and therefore CAMP goes down and protein kinase A goes down. I like it. And now, last but not least, I tell you, I told you I cut and paste this. Boom. Last but not least, we're going to do the same thing. We're in the membrane, don't forget. And now we have an activated G alpha GTP. And our activated GLTP, we're going to talk about GQ now. The activated G alpha GTP is going to do the following. Well, what it's going to do is it's going to activate the C's. This is all about the C's. We're going to activate phospholipase C. PLC equals phospholipase C. Phospholipase C will hydrolyze, use water to break apart a lipid, a phospholipid. And the phospholipid it finds is PP2. PP2 is a phospholipid. And PP2, we're going to cut off the polar head group, and the polar head group is IP3. And what lays behind after you cut off a polar head is a DAG, as in D'Agostino Groceries. The DAG stays behind. IP3 goes to the sarcoplasmic reticulum, which stores calcium. What's the purpose of sarcoplasmic reticulum? Store calcium. Sarcoplasmic reticulum. Store calcium. And IP3 binds to a receptor and opens up calcium channels. Calcium and DAG work together like bing bada. They convert protein kinase C from its inactive form. Oh yeah, got it. Woo! You guys are the only time I get to sing. Maybe Mia tells me, she says, "Daddy, stop singing." I don't want to hear that. I'll sing, Daddy. You can't sing well. So you guys don't get to say anything. So I get to sing for you guys. She's like, "Daddy, stop." I'll sing. I'll sing. I hear him singing. Just for clarification, this happens in the cell membrane, not in the mitochondrial membrane. That is 1,000,000% correct, Miss Alexandra. I love it. What's up, Samantha? Okay, so let's review it real quick. Ligand binds. GTP replaces GDP. That cleaves this thing. G beta, G gamma go on their way. G alpha, GTP activates phospholipase C. So the GQs, we're going to activate phospholipase C, which is going to cleave PP2. So there's GQ, GI, and GS. PP2. And we're going to cleave PP2 to DAG, and DAG stays behind in the membrane. IP3 leaves. And then we're going to get calcium, right? So we're going to increase our calcium. And in the end, we're going to increase protein kinase C. And that's going to phosphorylate a bunch of pathways. Know your G proteins crazy. Every step I just did, know insanely. And the last thing I want you to know about G proteins is the fastest way to inactivate it is to remove the phosphate. Remove the phosphate. Use a what? Phosphatase. Fastest to inactivate is to use a phosphatase. A phosphatase removes a free phosphate. So we're going to remove the phosphate to inactivate. Once you remove the phosphate, yeah, what happens? What does IP3 do? IP3 binds to a ligand and opens up calcium channels on the sarcoplasmic reticulum. DAG and calcium together activate protein kinase C. Thanks for clarification on that. I agree. Fast way to inactivate, remove phosphate, GDP, the glue is back, and then the whole gang gets back together and you inactivate it. I love it. Who doesn't love this? You should love it. Any question? That was good stuff. I dig it. All right, folks. Remove the phosphate from IP3. No, dude. Remove the phosphate from the G alpha GTP. No, yeah, no. Got it? That's good. All right, folks. Have a wonderful, lovely night, and I will see you. I suppose tomorrow night. Go back one slide to G. Yeah, can you clarify why that one equation you wrote was not oxidation reduction? Yeah, the oxidation numbers didn't change. Good night, Miss Catalina. Peace. See you in a few. Like 2 minutes. Can you repeat why the anomeric carbon? Oh my God, I'm getting really. Peace. Good night, everybody. Doris. That looks good. Wait. Where's that question? Good night. 7 million good nights. I love it. It's so nice to be loved. So whoever asked questions, of course they are. AMC full lengths are awesome. Dead on with the test. Can you repeat why the anomeric carbon in fructose is more oxidized than glucose? Yeah, the anomeric carbon in, you're welcome. In the anomeric carbon in fructose has 2 carbons attached. Got it? The anomeric carbon in fructose has 2 carbons attached, where the anomeric carbon in glucose only has 1 carbon attached. Ah, clear or unclear? Believe it or not? I believe it. Good. I believe it. All right. No, that's what we just did. Oh my God. Blueprint letters that are harder on par. Blueprint's awesome too. Blueprints are on par with AMC full lengths for sure. Except for the verbal. The verbal's a little messed up. But other than that, the sciences are dead on. Without a doubt. Dead on. Science for science dead on. Got it. You're welcome. All right, all right, all right. No, they suck. Don't do them. Don't do them. Well, I don't know why. Do blueprints. Do blueprints and do. I mean, I guess unless you get them for free, they're okay to practice, but they're just not on par. Got it? The thing. All right, everybody. Scott Roberts has left the building.
Mike, I need you to upload that thing for Lindsay onto